Hello everyone, welcome back to Advent of Code 2020. We're doing day 16 here today. Let's get started. Ticket translation. As you're walking into yet another connecting flight, you realize that one of the legs of your rerouted trip coming up is on a high-speed train. However, the train ticket you were given is in a language you don't understand. You should probably figure out what it says before you get to the train station after the next flight. Unfortunately, you can't actually read the words on the ticket. You can, however, read the numbers, and so you figure out the fields those tickets must have and the valid ranges for values in those fields. You collect the rules for ticket fields, the numbers on your ticket, and the numbers on other nearby tickets for the same train service via the airport security cameras. Numbers on... oh, I see. Together into a single document you can reference. The rules for ticket fields specify a list of fields that exist somewhere on the ticket and the valid ranges of values for each field. For example, a rule like class 1 to 3 or 5 to 7 means that one of the fields in every ticket is named class, and it can be any value in the ranges 1 to 3 or 5 to 7 inclusive. Your ticket is represented by a single line of comma-separated values. The values are the numbers on the ticket in the order they appear. Every ticket has the same format. Oh, in the order they appear. That seems important. Because if every ticket is the same, I assume we're combining knowledge about our ticket with other tickets. Here, this represents text in a language you don't understand, so we don't know what the field is called. This ticket might be represented as this string of numbers. Of course, the actual train tickets you're looking at are much more complicated. In any case, you've extracted just the numbers in such a way that the first number is always the same specific field, the second number is always a different specific field, and so on. You just don't know what each position actually means. Start by determining which tickets are completely invalid. These are tickets that contain values which aren't valid for any field. Ignore your ticket for now. So we're given these 3 rules, and every ticket has 3 fields, and so you kind of want to like match up for each of the nearby tickets. See for whether any single field is missing from all of the above. Like, for example, without reading their example, this one looks valid. 7 and 3 could both be class. 47 could be seat. Here, again, looks... ah, this is invalid. There's nothing... there's never a 4. Right? 40 and 50 could both be seat, or one of them could be row, but 4 is illegal. This... nothing ever goes as high as 55, so that's illegal. And in this one, they even helpfully highlighted for me, nothing ever uses 12. I see. Okay. I didn't notice the text effect there. So identify invalid fields in any ticket. What? Adding together all of the invalid values produces your ticket scanning error rate. Now that's interesting because they haven't addressed the possibility explicitly that a single ticket contains 2 invalid values. I assume, I mean, like they've described in text, yes, you should add it up, but I'm surprised the example didn't cover it as well to clarify that you should include both. Okay, so I did some thinking about this one before we got started, and I think it's reasonably clear what data structure we want. What we want is an efficient function from int to set of fields that int would be valid for, right? Yeah, and then when we're looking at tickets, we can just look at each field, and if any of them return an empty set, then we'll say, oh, that's illegal. And I think that data structure will be helpful for part 2 as well, which I assume asks me to somehow understand my own ticket, what all of the fields are, what fields each value corresponds to, by cross-checking with other tickets to find out which position means which field. In any case, knowing just like what fields are valid will be important for that too. So let's get started. And if you look, by the way, at our input, we can see a few interesting things. First of all, every field has two disjoint ranges, so we can parse those somewhat trivially. And there's one or two words at the front, but we'll just parse many words, it'll be fine. So I was thinking this would be like doable without using regexes, but I think it'll be a lot nicer with regexes, and we can avoid even doing any pre-processing of the input. We can just parse this entire single string with one regex, because the blank lines here are they stand out quite well. So let's write that regex first because it's something obvious and easy. What exactly are we parsing? We could like actually parse a map. Like this. Whoops. This we could understand as a map. And we could do that while parsing rather than like turning it into int ranges and then doing some post-processing on them, which seems like a fine approach, I think, to actually just parse it as a map so that we don't have to introduce any intermediate data format and then tear it apart moments later. So I think let's define data field, let's say, is a field of... I mean, honestly, do we even need to know the names of these things? We could just give them unique IDs, but actually we might need the names, right? Because maybe it'll ask you something like, what's your departure track times your price minus your row, or something like that, right? So we'll say field string. That's just going to be this thing here, and then an int map from... Oh, not from, it's just int, of course, to set of int? Does Haskell have an int set? Should I use one? It does have an int set, and it's in containers. All right. So we'll import data int map strict int map, import data int set strict int set, and we probably want to import each of those qualified as well. As m. There we go. So a field is a string and a map from int to set of int that's valid. And let's import just everything from TextRegex applicative again. And our input is it's several things, right? Let's just define a type, like an actual data type for input this time, because it's complicated enough that a 3-tuple looks kind of stupid. So data input is an input of list of field and also a single ticket. I'm calling it ticket. Is there any reason to do that? Should I just choose a vaguer name? Like, should I use like list of string? I'll call it ticket. A list of int, I guess. And then a list of tickets. And type ticket equals list of int. Int set is not it says here that it's in containers 0641. Do I have an old version of containers? I don't even know how I would find that out because like it's some stack nonsense. Stack just like picked it for me, right? Haskell stackage int set? I don't even know how to figure out. All right, I don't understand, but you know what? I don't care. I'm just gonna use a set of int. If that's what you want, set. Whoops, drop the as there. Okay, fine. Now, we don't want to write lines. Let's return a maybe int here because it might fail, right? And we'll have to adjust just like that. Yeah, that looks right. So it's just going to be match input, let's say, where input equals, and now we're going to define a bunch of little subreg(x)s and combine them. Hello? Oh, I forgot the key combo for looking at another file. There you go. So an input is a few things. It's let's call it inputs, actually. No, it's a single input, right? So input is an input, let's just write do again. We're going to read many field, and then a new line, and then actually instead of matching a new line, let's match string new line your ticket colon new line. Yours will be a ticket string nearby tickets others many ticket, and we're assuming ticket parses a new line at the end of it, so that's fine. Okay, and we just say pure of input fields yours others. Right, we called that thing input. Cool. Now let's work on ticket first because that seems pretty simple. Ticket equals do, I don't know. We'll have to implement set by ourselves. Actually, let's just it's int set by sim comma, I guess. Is that right? Yeah. And then ignoring a new line. We have to implement int and set by, of course. What is it complaining about here? Yeah. I'm surprised where it highlighted this. I thought it would highlight here is all. Int, we've implemented this many times, of course, but it's very simple, so who really cares? It'll be read of many esim is digit, which comes from data char is digit. And sep by of p sep equals let's see, p cons together p with many of parse sep and then ignore p. Seems pretty simple, right? And we just need field then. Field is kind of the most exciting one. Field equals do label many psim not equal colon. Why is it? It thinks the parentheses are mismatched again. It did this before when I had like when I was parsing things and it was totally fine. Now my indentation's all fucked. What the hell? It's annoying. Okay, anyway, sim colon. Actually, we'll just say string, right? String of colon space. Low high will be a range of int, I guess. Low 1, high 1, I suppose. Low 2, high 2. Actually, I could have range be the thing that turns stuff into maps, right? So we'll just call this low and this high. And I guess actually range shouldn't be, we should just call it int range because it'll only work for ints because we're building an int map out of it. High will also be an int range. And we'll finally return actually, an int range is returning what? A set of int? Yes. So we're going to make an int map m dot we want to say for each. I see. It doesn't help for int range to be a set. It might as well just be a list. M dot from. There's like a way to make int maps from lists that are already sorted. That's a bit more efficient. From distinct ascending list. Which will be, I guess, zip low added together with high with repeat label. Finally, we have int range is I'll just say do again, why not? Low is an int. You throw away a hyphen. High is again an int. And then we just return pure low high, like so. Yeah, why would I write? What's wrong here? A field is a field from string to inmap a set of int. Ah. So the problem is I said that I have a map from field to set of int. Wait. A map from int to field. What am I talking about? So what's the data structure that I want at the end of this? I want a good function that takes an int and gives me back a list of fields, right? So why do I have an int map to a set of int? It would just be like a set of int, right? Not an int map at all? I want an int map eventually, I think. Yeah. So we have a field. And a field Haskell data set. Let's look at this real quick. A set. I just want from list, I assume, right? Okay, I can use from distinct ascending list. Yeah, we're not zipping with anything anymore. And we're returning a field, so we should say field here somewhere. Field label this, right? Yeah, I'm pretty comfortable leaving. Okay, fine. No, I don't know. I get nervous about where. Anyway, I don't mind this redundant bracket. So we're not using int map yet, but I think we will want it once we get started on combining the data in our input. So let's just give these deriving show for a moment and say part 1 is just identity, and let's confirm that we parsed correctly. Wait, what? Whatever, it doesn't matter. I thought I was in the right directory for this already. Yeah, somewhat unsurprisingly, we parsed something wrong, and we can't really tell what. Haha, great. Here's one problem. Didn't put a space in there. Still wrong though. Yeah. I mean, I don't even know. Is there there's a trailing new line, isn't there? No, that's part of what we parsed in. Ah, hang on, I forgot that fields are supposed to have a new line at the end. And tickets already do. Okay. This probably doesn't fix it. It's probably more wrong somewhere, and I'll have to like... No, it works. Okay, cool. So we correctly parsed the entire input. There's our list of tickets. And at the front is a list of fields. And they're quite large, which is very, understandable. But you can see here we have, another key, which is departure station, and then another set. Cool. So it would kind of be nice, though, to actually adjust our input a bit more and actually parse out, create that the efficient int map that maps from int to set of field, right? So I guess, it would be nice a little bit if this were shared with part 1 and part 2, but I'm kind of content with this being not part of the input, but a simple derived thing they both share, and it's not too expensive to just do this twice. So we'll do it in both part 1 and part 2, I suspect. But it'll be a function that they share, but they'll both do the work. Slightly wasteful compared to an intermediate step, but okay. So what we have then, we want a function from, let's call it index, is a function from list of field to int map to set of string. That looks right. Index fields equals m dot unions with. We're going to construct a number of maps and then combine them. Yeah, that seems okay. Actually, we could do a little bit better here, I think. Well, I was going to say it would be kind of nice if instead of an int map of set of string, if we just had a function from int to set of string, and then we could do some cute stuff like automatically handle looking up in the set if it's not there, right? Giving a default value of empty if it's not there, instead of having to use m dot lookup with default or whatever. But actually, I think that's a bad idea because it'll make it harder to adjust the values in our index, which we'll want to do in part 2, I assume, once we're like proving, oh, okay, this, it's no longer possible for 7 to be the departure gate because we've already proven that it can't be, or something. I don't know. So I think representing the data in a more transparent way is still a good idea. So I think unions with, yeah, that seems fine. And then we're just gonna take like probably do, right? Do. And we're going to iterate over field. It comes from fields. And then, well, let's destructure this, I guess. Field label values. And yeah, we need a distinct entry in this map for each value, so we should pull those out, right? Value from, how do you get stuff out of turn a set into a list? I guess there's probably s.to list. Or elms, which is the same. Yeah. S elms of values. And then we're going to say m singleton. I assume that exists. Construction, yes, takes a singleton. Pure, I guess. Singleton of our key is the value, and the value is s singleton of label. All right, that looks good. So if we said now that part one is part one of field or input fields ignore equals index fields, do we get something nice? Yeah. So for example, we observe that 864 could be an awful lot of things, right? It could be arrival location, it could be a ton of stuff. But down at the bottom, 973 or 974, for example, can only be arrival station. Nothing else has a number that high. Great. So this should be all we need to do part one, right? Yeah, I would say rather easily. So it's input int is what we want, and we're just tickets. And we can honestly just ignore even the separation of values in between tickets and just like treat our list of int as a list of int. So it'll be sum of filter in fact, we don't even have to get something out and determine it's the empty list. We can just say like it's an m, you know, the map doesn't contain it, or the set, like, no, the map doesn't contain it. Yeah, which member is what that's called, right? Oh, there's even a not member function. How nice. Which takes not member index. We're gonna put index in a where clause in a moment. Of sequence tickets where index equal index fields. m.notMember, thank you, yes. Sequence from data control, well, we'll use sequence A, I guess. Which is in control applicative. And this compiles. Cool. Let's though. I mean, I don't know. We could run it, I guess. We might as well just run it and see if it gives us the right answer. It might be nice to test it somehow. Hello? What? Controlled applicative does not export. Oh, maybe it's just like. Is it in the prelude now? Okay, I guess it's in the prelude, which is nice. But it's the wrong type. So tickets here. Oh, I should be using. I'm using join, not sequence, right? I have a list of lists. No. Do I just want concat? Yeah, I just want concat, you weirdo. All right. I mean, it's a number. It's a little smaller than I thought it would be, but sure. How do I get you back here? Here we go. It's the right answer. Cool. Well, let's commit it. Hello? I can't type. That's not a problem that ever happens to me with a real Linux setup, right? This is just because I'm using Windows subsystem for Linux to give me my bash. But honestly, like if that's the smallest complaint I have with Windows subsystem for Linux, I'm still pretty impressed with it. Day 6. Oh, hang on. We don't need a Lambda case yet. I don't know. Maybe we'll want it for part 2. Day 16, part 1. Pretty straightforward, I think. Right? I mean, we had to write a kind of large regex, but I think it's very easy to understand, which is nice, and it handles the entire input file, so I don't know. Anyway, back to part 2. Now that you've identified which tickets contain invalid values, discard those tickets entirely. I see. Okay. Use the remaining valid tickets to determine which field is which. Determine what order the fields appear on the tickets. Okay. Look for the 6 fields on your ticket that start with the word departure and multiply them together. So, there's kind of like an optimistic approach, which is to hope that for each field, there is at least one ticket that has a value that could only be in that field, right? For example, here in this ticket, the value 1 could only ever be in class. And therefore, by looking at just this single ticket, we can say, okay, class must be the second field. And then what else? 3 could be like, it could be either class, no, it could be either row or seat. 9 could be either class or row. 18 could be anything. 15 could be any one of a number of things. 5 could be row or seat. 14 could be class or row. And 9 could be any of a number of things. I see. Okay, so even from this very simple input, we can tell the optimistic approach won't work. Yeah, and we're not supposed to look at our ticket. Our ticket is not supposed to help us figure out the order of fields. Nearby tickets should contain enough information. So we actually have to do like some elimination and say, okay, well, once we found out that the second field is... Actually, I've gotten lost. How did we determine that it's class? Right, because on this ticket, nothing could be class except for 1. No, that's not true. 5 could be. Oh boy. Now, just how many fields do we have? One very brute force approach would be just try all the possible orderings and then run each of them against each field and give up. But there's like 20 fields, and 20 factorial is a pretty large number. So doing even a small amount of work 20 factorial times doesn't seem like a good idea to me. So that doesn't seem like that seems like a non-starter is what that seems like. So I guess what we could do then is for each ticket produce a set of constraints, right? Where we say, okay, based on ticket 1, I know that position 1 is one of the following: row or seat, but not class because it's none of those. Position 2 is one of the following: class or row or seat. That tells us nothing. Position 3 could be class, could be row, could be seat. And then likewise for the next one, and combine all of those, and at that point there will presumably be at least one field that has only one possible one ticket that lets us say, okay, this... Can I really count on that to be true? It seems likely to be true, but not actually guaranteed. There might be some way that only by combining information from 3 separate tickets can I make any firm conclusion about any single field. In a kind of Sudoku kind of thing, right? Oh man, imagine. That sounds pretty horrible. I don't think it's going to be like that. I think once we build that set of constraints, we're going to be able to say, okay, position 2 must be arrival time. And then we can go through all the tickets that exist and edit their field 2 to say, well, it wasn't arrival time. and then look through all the tickets again, and hopefully wait a minute. Oh, and also go through all their other... It doesn't even matter what position 2 is anymore. We can ignore that from the tickets. But then go through all their other positions and remove arrival time from them and say, well, we know position 2 is arrival time, therefore 3 isn't, or whatever, right? And then look at all the tickets again, and hopefully there will be one that says, this position can only be this value, this field. All the same, it's kind of a tricky one to get right. There's going to be a number of ways to go wrong here, I think. And it's sort of a not super complicated algorithm, but like not trivial. Blah. Okay. Oops, wrong button there. Tried to switch back to this. Oops. Here we go. So part 2 is much more exciting. Do we care about... I think we should work only on... Yeah, we don't actually care about the order that the fields were given to us, right? In our input, we can just have like this int map to set a string, and then I guess we're gonna want another int map to set a string while we're working on this stuff, probably, because each ticket can be represented as a set of constraints, which would be represented as like an int map to set a string. Okay, so let's maybe define a type for that. Yeah, let's actually just make it a new type so it's harder to accidentally get wrong. Constraints is constraints of int map set of string. And index could return constraints, but there's no real need to, I don't think. Part 1 of input fields, yours, others. So first we need to filter out invalid tickets. So let's just start writing a big old let here. Let let's let index equal index fields. Oh, I just noticed, by the way, my indentation is working again. Why? It's a mystery. Anyway. Oops, that's part 1. Now that we've indexed the fields, what should we do? We should figure out which tickets are valid. Valid others equal filter all member tickets. In undefined, let's say, does that all type check? Oh, not tickets, but others. Yes, that type checks. I'm not using the results, but I didn't like mess up my filter or something. So we're looking at all the tickets and saying each of your fields must be a member of the index. Cool. And then what exactly? We need to like resolve the constraints somehow. I guess we probably want to write a function that takes a list of tickets and the field definitions and provides you an ordering. Like an order of what order they appear on the ticket, right? And it could just be a list of string. That would be okay. I'm not sure if it would be a convenient type for that function to produce, but as a consumer of that function, that would be a type I would be pretty happy with. So okay, let's let field order equal resolve constraints of fields of valid. Well, let's call this valid. In fact, mine equals zip your field order with yours, and then we want to multiply together map second filter. How do you write starts with in Haskell? Prefix of or something? Haskell data list prefix of? Is prefix of is in data list. Okay. Is prefix of departure is prefix of the first. Over mine. Okay. Well, it turns out that this all maybe could have even gone in where clauses instead of if, but I kind of like it as a little bit more procedural here. We need to import data list is prefix of, and then we need to write resolve constraints. That's the exciting part. What are you mad about here? Oh, it should return an int. Cool. So, I mean, we kind of just like spent a couple minutes doing the easy part and haven't really made any progress at all on the hard part. That's not quite true. We designed its API to return a list of strings. Resolve constraints is a function from a list of field and a list of ticket to list of string, right? Yes, that's the type I assumed it would have. Now I have to implement it, and it's very difficult. So I guess the first thing is we want to convert each ticket to a set of constraints, right? Or actually, I just called that a constraint, I think. Yeah. So each ticket is a constraint. Ticket to constraint is a function from ticket to constraint. Oh no, but that's actually it's a set of int is what I have here, because we only know about its positions, right? No. No. Set of string was right. Its positions are the keys in the map. The values are what set it could be a part of. Okay. So ticket to constraint of t we need more than just that. We need to know the list of field definitions, right? Oh, actually we need this, don't we? Yeah, maybe like this field of string to set of int is kind of a dumb type, because we immediately throw it away in both part 1 and part 2, which I was okay with, but actually no one else is using it at all. I don't know, it's still okay. Let's just define an index here. Type index equals int, no, yeah, int map to set of string. Oh geez, this is a problem because it's exactly the same type that constraints has. Well, that's why I made constraints a new type, so I can. Okay. So we don't take a field, we take an index. So then what we say is it's constraint of m dot from what do we call it? Distinct task list is the thing of do, I don't know, whatever. I comes from zip 0 with t. That'll be the key in our constraint. And then we're going to look at the index. Are we just calling the index and that's it? Yeah, we're calling the index on our IV, and then we say probably I think pure of I and m dot find with default s empty of v and index. Call to constraints. Okay, is this type checks? And the funny thing is, most of what I wrote here is just like completely useless. I just re-implemented fmap, right? because we're leaving fmap for tuples applies a function to the second element of the tuple, and we're not sharing any information between I and V. So if we wanted to rewrite this, how would it go? It would be like constraints m dot from sync to sending list map fmap something like let's zip 0 here, and then we don't even need to do the fmap. If we zip the 0 later, we can just map a function over the tickets, which is like it's this, but just juggled around a little bit. Flip so I think it's like just this basically. Oh, yeah. This is actually kind of nice, I think. Indented like that. I don't know. Is this easier to read than what was there before? I don't think so. All right, let's put it back. All right, just wanted to like at least write that out and see how it looks. Now that we have a list, we can get a list of constraints now. This is one of those cases where I wish I had a stepping debugger, just so it's easier to look around at what my data looks like after I've made partial progress on a problem to ensure things are okay, rather than just like continuing to program with blind faith and then running a program and seeing, oh, you got 0, great, or an infinite loop, amazing. So I think what we'll do maybe is well, we should work on resolve constraints. And do we even care about the fields? We don't. We're passing it the index anyway. Oops, this is called an index. Index t's. Okay. So we're going to do a few things. First, we're going to let c's equal map ticket to constraint of t's, ticket to constraint of index over t's. And then I kind of feel like we just want to we want to iterate with like a set. We're iterating, obviously, over the set of constraints, and we're going to update them each time we discover what position a field is at. But what other data do we need to iterate over? I think it would be nice to have like a set of fields that we've already resolved, so that I can, if I find a ticket that says, oh, I figured it out, position 2 is departure time, we can be like, yes, I knew that already, like, shut up, right? So I think all we really want here is in go of s empty and C's, I think, where go of resolved fields yeah, and I don't really need to keep track of what position we actually resolve the fields to, because at the end all of our tickets will say on the set of constraints for the ticket will be, okay, position 0 must be departure time, position 2 must be arrival gate, and so on, right? So we can actually just have the list of tickets be the constraints that the order. We'll just look at the first one, for example, and pull out its ordering. Well, actually, let's just inline this variable and everything gets much easier. Whoops. Okay. So that makes sense. That type checks. Now, do I want to track resolved fields? Maybe I should track unresolved fields. Does that matter? I think resolved fields is fine. We'll just keep going until one of our tickets tells us what position everything is at. And what is our constraint again exactly? It's an inmap to set of string. Okay, well, we need a stopping condition first. So we say when any of the tickets have the property that all equal, well, let's call it all. We assume all tickets will resolve at the same time, and this way we don't waste work checking more of them if the first one fails. Equal 1 dot length of we're holding a set of constraints. Okay, so let's give that a name here, so we can, there's just a function to get a constraint out. So if all the tickets are, actually, you know what? We'll do it like this, and we'll say if on the very first ticket, the first constraint is resolved, then, I don't know, undefined, like, is this even legal? T0 constraints? expected type. Why do you have some weirdo? Why do you think there should be a foldable of constraints or something? So what's hang on. It thinks I'm somehow folding overseas with this all, which of course is incorrect. What I meant to do is get out the constraint and then fold over that. Like so? Okay, and then I can do it like that. So looking at the constraint C, are all of its values singletons? If so, we must be done, right? And if so, we can actually return a meaningful value and say, actually, we're going to use this pattern in the other pattern. Is we need to return a list of strings, and I think that's just, since the mint map is in order, we can just like look at 0 and then at 1 and so on. So we're going to look at the elms of C and then do something to that. That'll be a list of singleton sets of ints. Singleton sets of strings, I mean. I guess we'll map S to list here and then concat the results. Okay. Yeah, you're gonna tell me concat map, I should use concat map. That's probably fine. That's fair. Okay. So that's our base case handled. This indentation style that I'm using looks highly cursed. I mean, I guess it's serving its purpose, which is to give me plenty of space to write the equations after having written the guards, but it feels pretty gross. Well, okay, one thing I could do, I guess, it doesn't help with the problem, would be to like do that. So now what I want to do is scan the tickets. Let's say I kind of want to map a function over each constraint and let it return a maybe, where it says just if it knows how to fix how to resolve another constraint, and returns nothing if it doesn't. But actually, why mess with maybes, right? We're already in list. It can just return a list of things by mapping over each of its constituent positions, right? So let's case. I still think I want to like convert that result to a maybe though. list to maybe of... Oh, is there like a... Do I want map maybe? There's a function called map maybe, right? What is that? Map maybe. Takes a function from A to maybe B and a list of A and gives you a list of B. Yeah. So what I want to do is map... Map a function... Yeah, I don't know, like, if they each returned a list, like, wouldn't it just be concat map and that would be fine too? I'm just like, my problem is that here at the top level, I really want there to only be one result, even if I happen to find multiple, right? And so converting the list to a maybe at some point would be nice. So I guess what I should do is concat map a function over each ticket, or each constraint, but then at the end convert the result to list to maybe, which is what I started doing. Okay. Concat map resolve, I guess, over C's of nothing, error busted, right? We found, we determined that we're not done. The first ticket can't be resolved completely, and there's no single ticket. I guess what I might as well do, gave up after resolving only show resolved fields. Okay. And then if we say just new I label, then what we will do is we will go of s insert label resolved fields and map solved label over C's. Okay, so we have a few functions to implement now, and one to import. Where, actually, you know what? Solved could be at the top level here. Solved of label C's equals, or constraint M equals M, actually it's just fmap, it's constraint of fmap s delete label over M. Constraints. Yeah. So we're gonna map over the constraints we have, and if it says, oh, my position 3 could still be departure gate, and we know departure gate's been resolved, we're just gonna say for every key you have, oh. So problem with this, is that we will then have deleted all knowledge of departure gates, and we'll have forgotten what position it was at. So I actually need to do a bit more here. Solved I label, let's say. It's constraints of we're going to fmap that, but also then s insert, no, m insert I of s singleton label. Okay, that makes more sense. Right, so we're gonna delete from all of these existing constraints the possibility that it could ever be this, and then overwrite the constraint for the position that we've solved with, well, it must be this one thing exactly. And finally, we just have this resolve function. Resolve is a function. Resolve though has to be here. It has to be inside of Go, where, yeah, that's the right place for it. Resolve constraints m equals filter s singleton second of m assocs m. Oh, right. Do we have a good way to test for singletonness? We just have like length equal 1, huh? Well, let's pull this out to a new function. Is singleton is a function from set of a to bool. And there's a more efficient way to implement this, I'm sure. Oh, probably we should be using s.length, because length is really? Oh, size? Yeah, because length will work on a set, but not at all efficiently. It'll iterate the whole thing. And s.size should be efficient. What are you mad about here? Okay, we need to give a type to solved because it clearly doesn't agree with me about what type it should have. Solved is a function from int and string and constraints to constraints, right? Resolve is what needs a better type. Resolve was meant to be a function from constraints to a list of pair of int and string. That's why this is wrong, because I'm returning the entire set, not just the second element. So so now I want to say map fmap head, not head. Bleh. Okay, gross. We don't want to do this as a map and a filter combined, I don't think. Let's just do I x's from m to SOAX m guard that is singleton x's. If so, return. This could be a list comprehension. I know. Pure of I. How do you look up like min max or something? Find min or something? Sure. S find min x's. Wait, hang on. We have a set. A set of string. I guess that's fine. Okay. Well, really? What do you? Pattern matches are non-exhaustive. I mean, that's true, but there will always be a non-empty list of constraints, so I'm okay with that. So we wrote a big pile of junk that compiles. I honestly have no idea if it's correct. I assume not, but at least running it will give me some feedback on what's going on. Gave up after resolving nothing. Well, that's not promising. Okay, I should list some of these things out into top-level functions so I can test them. Resolve, for example, doesn't use anything from its local closure. And therefore is very easy to test. Oh, I guess I wanted to delete this entire rectangle. So let's see if that even works, right? Oops. Let's say if we said resolve of constraints, and what's my constraints again? It's an int map m.from list of, let's say at 1 we could have either A or B, and at 2 we have B or D. Oh, ugh. These are lists and I need sets. Zip with map s.from list of, there we go. Wait, this isn't right either. Because, oh, I'm just giving it a single constraint. Yeah, that's fine. Of so at position 1 we have A or B. At position 2 we have B or D, and at position 3 we have just, let's say, C. Okay, so it successfully says, yep, here you go. It should be I mean, I guess what I should have done before implementing this entire algorithm was just like work it through in my head on the example given in the problem, right? Would this even work on what's given to me here. So we did part of it before, right? We said that well, did we? 14 was, no. The problem was, right, none of the actual fields none of the tickets have a single specific field that could only be one thing, as I recall, right? Right, this 3, it could be row or seat. The 9 could be anything but class. It could be anything. The 18 could be any of these. The 15 could be any of the large ones. The 1 could be a small one. 5 could be row or seat or class. 14 could be any of these 2, I guess. Yeah, so you kind of have to do a little more local reasoning about a ticket than just look at each of its fields completely separately. Because on this one, the 14 could be class or row, and importantly, it can't be seat. And so either 5 or 9 must be seat, but either of them could be, so that doesn't really help that much, I guess. Okay, which of these are we supposed to actually make progress with? 18 is no good. It's always can be like any of them, can be 18. 9 could be any of them. 3 can't be class. So these 2 have to both be row or seat. But they could go either way, right? 9 could be the row and 18 the seat. Or 9 could be the seat and 18 the row. So the first ticket doesn't give us any clear indicator. For 15, that could be any of them. 1, well... Oh no, hang on, 15 couldn't be seat. And 1 could be any of them. 5 could be any of them. I see. So what we really should do is we've proven that the first position can't be seat by looking at 15 on this ticket, right? And we should propagate that to all of the other tickets. And then on this one, when we say, you know what? 3 can't be class. The first position can't be class either. Then we'll know that it must be row. Okay. So, can we do like some intersection stuff here? We take, like, I don't feel bad, by the way, about like writing all this stuff and then realizing my algorithm doesn't work, because a lot of this is reusable. Well, I don't know, maybe not. The like termination condition is fine. Solved, I think, is also fine. It's just this like this part that needs to be rewritten, and this resolve function that it works on that doesn't matter we're not going to use anymore. But is singleton is probably still useful. Maybe? Yeah, because we're using it at least here, if nothing else, right? We just need a better way to make progress on actually resolve was never any good, was it? Because I forgot to ignore positions that we already knew the answer to. But we have what if it's really fucking easy? Like, that's just possible, right? It might just be that I have to intersect all the maps values and everything just falls out. I'd be interested in seeing that. What do we get from that? It probably won't be a complete solution. I expect we'll have to do some work where we say, okay, position 2 could be A or B, but we know that position 1 is A, so position 2 must be B. But I bet we get a lot of progress just by like intersecting all the maps, right? So what if we do that? What if we said that part 2, let's like write a new part 2 briefly here. Part 2, actually, here's a thought. Why don't I just write a function called debug or something? And define debug of this in we have our index, which is an int map of set as string, and I think oh right, well, we needed a set of constraints. Ticket to constraint of tickets. C is equal to this. Others. In M, I have a okay, let's look at int map. What functions do we have for combining stuff? Combine. Union with and intersect with should be the same because they'll all have the same keys, right? So we'll just say union with, I guess. Union with S intersect intersection. That exists, right? Yeah. Union with S intersection of M, where M M where constraint M comes from C's? Constraints M? M union with what? Oh, unions with. Okay, so like, oh, problem. Part 2 is broken. That's why part 2 just calls error. Right. So maybe this should have been part 2 to begin with, huh? Get rid of this weird debug thing. Hello? Get rid of the X? There you go. So if we ran this, what would we determine? What would we learn? from list. Well, this is just totally junk, right? What the hell did I do wrong here? It said no position can be anything, except like 11 could be everything. What? Why is 11 special? I mean, we've already done this before, but I kind of want to in C's and just make sure this came out okay. I don't know. Why pipe it to less when you're already in a terminal emulator that lets you scroll? I don't know. It's a mystery. Constraints are not showable, are they? That's what's wrong. I mean, this looks reasonable, right? This ticket says, oh, you know, 4 could be any of these things. Are there any of these that don't end with zone, for example? That would be nice to know. I mean, okay, the point is that these all have a bunch of values. It's hard to argue with that, right? Ah, something's wrong. Look at this. 1 can't be anything, it thinks. That's scary. That should never happen. We're looking. Oh, I forgot we're supposed to look at only valid ones. Did I forget that in part 2 as well? That'd be very important, wouldn't it? No, I filtered it. So let's let this happen. And then maybe this would give me a more instructive result now. Okay. Yeah. Look at this. 18th position must be class. And I bet there's one in here somewhere that like has only class and it's like size 2. It's got like just a class and one other thing or something. Class row, here it is, 13. And then I bet there's one that's got like size 3 where it could be like class or row or something else. I'll do a quick visual scan just to like confirm this idea. But it should be fairly class row train, that's 0. Okay. So I think this is what we were meant to do, is intersect them all together. Which is a generalization of what it will discover all of the answers from my earlier algorithm, but also many more. So this is a much better approach. And I assume there'll be one with class row train and something else. Yeah, look at that. Index 1, class row train and type. Here, right? So this looks great. So we just have to fix up resolve constraints. Fix up like this case, right? Using the information from I actually probably want this. Yeah. Let's say resolve. We'll just change the type of resolve. We won't map it over all of them. We'll feed it all of them at once. Resolve. Resolve fields C's. What are you mad about here? Oh, resolve has the wrong type now. Sure. So, well, yeah, resolve now takes a S set of string and a list of set of constraints. Resolve, and now this type checks better. Okay, so resolve of done and C's equals. Now we can borrow some stuff from our little debug thing here. So we have this let fixed, I don't know, equal this. We'll just do a list comprehension, I guess. In do, I never know what I'm gonna write. In do, God, what a weird structure to write. Let's just do let fixed equal this, and then we'll say I possibilities options from m dot associates fixed guard that is singleton options guard furthermore that not s dot member, oh hang on, let field equal s dot find min of options, then guard that the field not s member field done, finally return pure of I field. Okay, that seems good. So now we're intersecting each ticket together to reduce the problem space rather than trying to look at a single ticket at once. So what happens if I just run this? Am I going to get anything useful? Probably not. Woo! It solved. It finished. It got them all. All right. Well, that's the right answer. Okay, great. Well, this is a tough day, but not unbearable. Anything I should resolve here today? We needed applicative do. We don't want this junk. I gotta say, this is not like a solution that I'm proud of necessarily. I don't know. It seems like pretty wordy for what seems like sort of a simple problem, but maybe this is just a a consequence of my insistence on writing a reasonable domain model. I don't know. Because I feel like resolve constraints is actually not that bad. And that's like most of the, I don't know. Anyway, whatever. I'll just stop dithering and then commit this, shall we? Day 16, part 2. All right, let's go just look at the advent calendar real quick. Just see how the map is shaping up. I notice it's not leaving gaps in. It's just doing stuff out of order as we backtrack. Okay, fine. And where are we now? We were here. Tomorrow we'll be here? I don't know. That's tracing out our path, which is kind of cute. And these are ports that we visited, I guess. Anyway, that's all for today. Hope you guys enjoyed. Thanks for watching, and I'll see you next time.